Since the earliest days of astronomy, since the time of Galileo, astronomers have shared a single goal: to see more, see farther, see deeper. The Hubble Space Telescope's launch in 1990 sped humanity to one of its greatest advances in that journey. Hubble is the telescope that orbits Earth. Its position above the atmosphere, which distorts and blocks light that reaches our planet, gives it a view of the universe that far surpasses that of ground-based telescopes. Hubble is one of NASA's most successful and long-lasting science missions. It has beamed hundreds of thousands of images back to Earth, shedding light on many of the great mysteries of astronomy: the age of the universe, the identity of quasars, and the existence of dark energy. But have we finally reached an age where this wonderful piece of technology might finally see its last day?
No way, this can't happen. What about these beautiful pictures?
Aha, I feel a calling for another recruit. I'm on my way.
What? Who are you?
I'm Mark, and I'm from the Saving the Hubble Telescope organisation. I've got something to show you. All right, listen up, recruits. It's Vexperts here, and we've received a new mission from SpaceX. Our mission is to save the Hubble telescope before it dies, and then bring it back to Earth so we can recycle parts from it.
Our idea is to send the Falcon 9 rocket into space, loaded with a net which will capture the Hubble telescope from behind it.
It will then return to Earth with the help of the first stage boosters. We also had to calculate the dimensions of the net, so it's big enough for the telescope. The net is 20 by 23.5 metres big and has a mass of 4,068 kilograms. However, launching the rocket itself requires lots of maths and physics. In order for the rocket to go up, the speed obviously has to change and increase. The amount it needs to increase is called the change in velocity, delta V. This is what we are trying to find out. For this, you're going to need the rocket equation.
Delta V equals VE times Ln times MO divided by MF.
If we want to understand the equation, we have to look into depths with each of the variables. Exhaust velocity. If you want the rocket to go up, something has to come down. This is Isaac Newton's third law. Every action must have an opposite and equal reaction. If the rocket is to go up at 2 kilometers an hour, then the fuel has to come out at 2 kilometers an hour. This is exhaust velocity, the rate at which the fuel leaves the rocket. We also need to remember to multiply the exhaust velocity, which is 300, by the gravitational constant, 9.8. This converts it to meters. Number 2. Natural logarithm. This is the time it takes between when the rocket is full of fuel and when it is empty. It's very important because if you run out of fuel before you reach orbit or have too much of it, then the rocket is just going to fall back to Earth or be too heavy to stay up in orbit. Number 3. MO divided by MF. MO is the mass of the rocket when it's full, so with the fuel and the payload. This is 606.8 tons. And MF is the mass of the rocket when it's empty without the fuel. This is 171.8 tons. This equation is used to determine multiple things: how much fuel you have, or how big the exhaust has to be in order to get the fuel out in time. So we plug in the numbers and we got 3,710 meters per second. This is the speed we need to reach.
It's very important to get the rocket up into space, but it is important not to forget that we have to also get the rocket into orbit, so it's at the same level as the Hubble telescope.
When the rocket is in orbit, it has reached such a speed that it's always falling, except it's falling parallel to the Earth, so it never actually touches it.
There is another equation for this. Orbital velocity is equal to the square roots of gravitational constant times mass divided by the distance from the centre of the Earth to orbit.
Once again, we plug in the figures and we get our answer, which is 7.5 kilometers per second. So now you are in orbit. All you need to do is turn on the engine and achieve the second or third burn to speed up the rocket enough to catch the telescope. To come back to Earth, you just need to slow down the rocket and you will slowly fly back. This is how we're going to save the Hubble telescope, one STEM at a time.